When you upload one video file to your system, behind the scenes, it automatically creates 5 separate indexes from that single upload. You have vector embeddings for semantic search, object detection for visual search, transcriptions for text search, audio features for sound search, and then finally, metadata for pre-filtering. Each of these indexes is optimized for different query patterns. This is what we call object decomposition, and it's how production multimodal search actually works. Let's show why this matters. Let's say you're building a product search engine for an e-commerce site. A customer uploads a photo of a shoe they saw someone wearing and asks, find me red running shoes for cold weather. Now, that one query actually requires 4 different types of searches working together. You have visual similarity. What does it look like? You have color matching. Is it red? You have category classification. Is it a running shoe? And then you have contextual understanding. Is it suitable for cold weather? So if you index that product image, it's just one thing, the embedding. This is how most people do it today. One database entry, and you can actually answer long tail complex queries like this. You should actually decompose that single image into multiple searchable layers. And that's the problem that we're uncovering today. So here's the architecture. Every file you upload is an object at the top of a hierarchy. That object gets decomposed into documents. Think of these as logical slices of content. For an image, the document might be the full image itself or segmented objects within it. For a video, these documents could be individual scenes. For a PDF, these documents could be pages or sections. Then each document gets decomposed into features. Features are the extracted insights. These could be the embeddings, the detected objects, the colors, the text from the OCR, or the brand logos. Each feature type goes into its own specialized index. This gives us layered indexing. Layer 0 is the raw object. This is the source of truth, the original file. Then you have layer 1. These could be the documents, so scenes, pages, segments. Layer 2 is the features from within these documents. These could be the embeddings, the objects, the text. And layer 3 could be specialized index for each of these features. So as you can see, we can expand these layers as we go down the tree to make it more and more comprehensive in what we want to expose for our search queries. So with this architecture, one single file upload actually powers a ton of different queries that span all of these different layers. So you can search by semantic meaning, by specific objects, by color, by text, all from the same source file. So let's walk through a real live example. This Nike Air Max product image, we say it's layer 0, it's the raw image file. Again, the source of truth. Layer 1 is we could run object segmentation to isolate the shoe from the background. There are some really impressive state-of-the-art models that are only recently available, like SAM2 from Facebook's Meta Research Lab, that does this quite well. And so now we have 2 documents, the shoe and the background. For each document, we extract features. So on the shoe object, we could run a clip embedding model. So this is a 1500-ish dimension vector that captures the semantic meaning of the object that we pulled out from the image. Then we have object detection. So this could actually create bounding boxes around various things that we want to pull out. Shoe, sneaker, footwear. Then we have color extraction. Dominant colors like red, white, gray. These are very standard classification models, and they're not new at all. But the really innovative thing that we're doing here is we're chaining these models up to create all of these different layers, right? And then we have OCR. So again, nothing new, but we could pull out the text that's visible in the shoe, Nike Air Max 97, etc. Then we have logo detection. Again, a classification model. Nike swoosh is identified at these specific coordinates. The really innovative thing here is that because we're using all of these specialized models, all of these task-specific, domain-specific models, each of these is independently fine-tuned. So we can say, hey, we want to improve the object detection model in these specific characteristics, and we want to improve the OCR model in these specific characteristics. So we can fine-tune them independently. And then again, because we're creating all of these different layers, these different indexes, our search queries can capture all of these learnings that we've found as we navigate the system. So in the next layer, each of these features actually gets its own specialized index. So the embeddings go into a vector database. These are your pine cones, your quadrants, etc. The objects can go to a spatial index, so GeoJSON. The colors can go into a specialized index, maybe a color palette index that has tuples. We have text that goes into a full text search index. So this is your TF-IDF, your BM25. And then logos can go into just a very standard metadata store for classification. So now, when someone searches red running shoes for cold weather, your system can hit the vector index for semantic similarity to running shoes, hit the color index for red, hit the text index for product descriptions that mean running or weather, and then hit the object detection index for shoe categories. And then because we actually are running a search across all of these different indexes, we can join all of these results together on query time. And so we call this decompose on write, recompose on read. And this is actually how you unlock complex, long-tail, natural language queries on structured data. So let's talk about what it takes to build this yourself. So obviously you need to upload the file into some store. That's typically S3 or some other object storage. Then you need to run 5 different ML models. You could have SAM2 for the segmentation, CLIP for embeddings, YOLO for object detection, a custom RGB extractor for colors, Tesseract for OCR, and a fine-tuned logo classifier. So each of these models actually are often open source, but actually running them and maintaining them, you can do it locally, but if you want to parallelize or run GPU acceleration, you typically need to use something like SageMaker or Ray or Modal. So, but maybe you want to batch all of these requests in order to saturate your GPU. So this is where a distributed compute framework like Ray or Spark or Daft comes in. So we have 5 different outputs from all of these different models. So where do they go? So the embeddings, again, they can go into a Pinecone like vector database or a Quadrant or Milvus. And then we have objects. These can go into a spatial index. So Elasticsearch actually supports that. So does MongoDB. And then we have colors. So this can go into a SQL store like Postgres or MySQL or SQLite. Then you have text. And so because, again, we're using TF-IDF or BM25, these sparse vector indexes, we could use Elasticsearch or maybe even Algolia. So then we have logos. Well, where does that go? Well, that could actually go back into Postgres, and maybe that is a foreign key that we link up on retrieval time. So now we have these 5 different database connections, and each of these uploads actually requires that we write to 5 different writes. Each query requires that we read from 5 separate reads. And then again, we are manually joining all these results together. So typically it requires a little bit of network egress, ingress for write and read. But what if a database goes down? Then your search is broken. A schema change, then you have to rewrite code in all these different places. Or maybe you want to actually run a new feature extractor. So you have to run a new database, and you have to recompose a new model into the pipeline. You have to update the actual underlying vectors, migrate them from one vector configuration to the next. So this is all orchestration code that actually requires you to keep everything in sync. And we haven't even talked about data lineage. How do you actually trace back the feature to the original source? Teams often spend 6 to 9 months building the infrastructure to support this composability before they can even start building their actual product. So this is how we actually do it at Mixpeek. At the top, we're just importing our client, and then we define our collection. And collections are composed of different feature extractors. And this is really important because feature extractors are actually built, managed, and maintained by the Mixpeek team. We have versioning and all of the stuff that you'd expect from a production system, but it's really important because under the hood, we can upgrade the clip model, we can help fine-tune the clip model, we can use the latest and greatest YOLO model, the latest and greatest SAM2 model without any disruption to your system, because since we're managing the actual feature extractor pipelines, we can do the migration for you under the hood. And so all of this is abstracted, all of this orchestration logic is abstracted. So we just define these feature extractors, we create the object, or the bucket, we'll say, and then we upload our objects to that bucket. And maybe we include some metadata to make it more business specific, right? And so every time we upload the object, because we connect the collection to this bucket, that object gets decomposed using all of these feature extractors that we've defined in the collection. And so this is what then allows us to build these multi-stage retrieval pipelines. The first stage could be a standard KNN search. We call this feature search. It could be a hybrid search, span multiple features. And then the next is maybe an LLM enrichment. Maybe we want to do filtering on all of the documents from that previous stage. And then the third could be actually a join from another collection or from this collection. So that allows us to actually recompose all of the resulting documents by the uniting object ID. So that's the original source. So that's it. We actually achieve everything that we talked about in 10 lines of code. So we have a single API call that handles multiple database connections. We have an upload that creates 5 specialized indexes. And then we have the Mixpeek system, which runs all the extractors in parallel, auto scales the GPU resources and the batching, stores each feature into an optimized index, gives you recommendations on creating indexes as your query patterns evolve, and we have the ability to track the entire data lineage from feature to document to object to source file. And then obviously handling everything that you'd expect from monitoring, error handling, retries, etc. And so again, when you want to search, it's as simple as executing the retriever. Red running shoes for cold weather right here. And then we just supply the collections. So again, the system actually automatically routes your queries to the relevant indexes, merges the results. So if you're using hybrid search, it does what's called reciprocal rank fusion, returns the documents with the complete lineage, and the query latency is sub-second. So because each query hits the index it needs, it doesn't have to hit all of them, we can actually shave down a lot of the latency that we'd expect otherwise. So what previously took 6 to 9 months to build, you've just deployed in less than 5 minutes. So let me show you this visually in the Mixpeek Studio. Here's a collection. You can store all of the objects that we've just uploaded here. And if you expand this object, you can see all of the documents. The segmented shoe object with all its metadata. And then if you expand again, you see each feature that was extracted. We've got the clip embeddings. These are the actual vectors. The detected objects. These are the shoe, the swoosh with bounding box coordinates. You've got the extracted colors. These are the RGB values and the hex codes. OCR text. So this is the Nike Air Max 97. You've got the detected logo. So again, all of these models are individually fine-tunable for the individual access patterns and the data sets that the user has. We can swap out any of these models under the hood, and then the migration to new indexes is seamless. This is a big challenge in vector databases when you have all of your objects that have been embedded using embedding model A, and when you want to use embedding model B, you actually have to re-embed everything, migrate everything, and then swap all of your queries to the new system. And then what if that new system doesn't perform as well? Then you have to re-migrate everything back and then use the previous index. So all this migration and cutover and A/B testing and all of that is handled for you. And the most powerful part about all of this is, from an auditability standpoint, you can trace any search results back to its original origin. So this result came from the clip embedding, which came from this shoe object, which came from this source file uploaded on this date from this S3 bucket. So we have the complete data lineage automatically tracked. One more thing before we wrap this up. This layered structure isn't just about search. It sets us up for something even more powerful, and that is what we call taxonomies. Because each feature is linked and typed, we can enrich documents with semantic joins. Joins in Mixpeek are just retrieval operations on another collection. So our logo detection found a Nike swoosh, and we can automatically join this image to a product taxonomy that we built separately. So that allows us to categorize Nike to footwear, running, Air Max 97 to red colorway. Now, every layer doesn't make search faster, it makes these relationships explicit. Now, this is really important for businesses because it allows you to define guardrails that are specific to how your data is structured in your use case. And we'll cover taxonomies in a later module, but just know that the object decomposition is the foundation that makes taxonomies possible. So remember, 1 upload, 5 indexes. Each index is optimized for different query patterns. This is how we can go from searching from keywords to search by visual similarity, color, brand, context, and metadata in a single query. It's the difference between a very simple demo and production-grade infrastructure. So later on, we'll dive into feature extractors and we'll talk about all these different models that power all of these different indexes. We'll talk about clip versus blip and how to chain these extractors together and how to pick the right model for your use case. All of this code, by the way, it will be available in GitHub and it'll be in the description below. And if you're building multimodal search, you can try Mixpeek for free at mixpeek.com. And thanks for watching Mixpeek, it's Multimodal University. Thank you.